Hello, everybody. Thanks for joining. We'll give it a couple more minutes before we get started. While we wait for more people to join, we can go ahead and kick off. Hi, everybody. My name is Jenna Brown. I'm an Associate Program Manager for USCRP. Thanks for joining our June USCRP monthly meeting. Before we get started, I'd like to begin today with a brief overview of the program for those of you who may be new. USCRP began its formation in 2014 because we were seeing a decline in coastal research in the US with less students pursuing advanced degrees in coastal sciences. We also saw a need to better communicate coastal hazards to local coastal managers and the public. The USCRP received funding and an associated congressional directive specifically to address coastal processes advancements that targeted improving our understanding and ability to predict nearshore coastal processes. The funding was specifically directed for academic researchers to address prioritized gaps in federal research and to begin to collaborate with federal researchers, thereby expanding our research dollars. Today, you'll be hearing from USCRP funded projects working to address these prioritized gaps. So before we get started with our research presentations, we'll kick it off to Nicole Elko, one of our co-executive directors of USCRP, for any announcements. Nicole?
Thank you, Jenna. Hello, everyone. I'm Nicole Elko, one of the co-executive directors here. I'm the executive director at the American Shore and Beach Preservation Association, fulfilling the stakeholder role in the leadership team. And I have a couple of exciting announcements. First of all, it's great to see such a good turnout today, obviously in part to our amazing speakers that we're excited to hear. So thank you for joining us. For USCRP announcements, we did receive funding in FY26. We're excited, unlike FY25. So we were able to award 6 projects this year and help them to continue the work that they had been elected to do through the program. We will be updating the dashboard soon with all of those projects and where we are as of FY26. So that was great news that we're excited to share with you. On the conference front, we are sharing out the outcomes of the decadal workshop that USCRP hosted a couple of years ago now. And the most recent presentation on that was given in Galveston at the ICCE. For any of you that attended, you hopefully got to hear Dr. Hillary Stockton give a great talk on the next decade of USCRP and how far we've come. The next time that we will have an opportunity to showcase USCRP at a conference is coming up this October at the ASBPA conference, National Coastal Conference in New Jersey, which is our centennial celebration. So hopefully you all got your abstracts in to join us. If you haven't, pro tip, the abstract portal is still open today to submit an ASBPA abstract. But it says it closed yesterday, so insider knowledge right there. And then finally, the dedicated issue of Shore and Beach, which includes the papers from that decadal visioning session for USCRP, is about to hit the presses and it will be issued this summer. So that's all from USCRP. Just a reminder though, if you all have any announcements of events or things coming up that you'd like to get out to the coastal research community, please share those with us. We can share them on these meetings as well as in our monthly newsletter. Thank you so much. And back to you, Jenna.
Awesome. Thanks, Nicole. Those are great updates. And yeah, we like to hear from everybody. Even we see in the chat, there might have been a calendar issue. So yeah, we'd like to hear about anything and everything from our members. And so with that, we'll go ahead and kick off our presentations today. We'll have 2 presentations. Please stay muted when you're not speaking, and you can feel free to enter any questions in the chat. We can get to those as time allows. And with that, we'll start with our first speaker, Dr. Peter Ruggiero from Oregon State University. and talking about a probabilistic framework for modeling compound flood hazards under climate change. So go ahead and take it away, Peter.
Great. Thank you very much, Jenna, and thanks everybody for coming today. Definitely want to acknowledge funding for this project from the USCRP, but also to say that we've leveraged a couple of additional funding sources from the National Science Foundation to their Coastlines and Peoples program as part of the Cascadia Coast Hub, as well as some research we're doing with ERDIC of the U.S. Army Corps of Engineers. And so I'll be talking about the title that Jenna just mentioned. This will be a focus of Yaquina Bay, Oregon, on the north central Oregon coast. And a few of the team members are, I think, on the call, but I'm going to just kind of go through them so everyone is aware this is a very collaborative effort. David Roop is a professor on the left-hand side in the college that I'm in at OSU. Felicia Almeida Schultz is a hazards extension agent with Oregon Sea Grant. Catherine Hegovich is one of the developers of the Climate Toolbox, and some of the tools we're developing are co-developed with Catherine. Then the next two folks are Nate Philman and Carson Williams, who are both PhD candidates here at OSU, who've done the vast majority of the work that I'll be talking about today. Estella Carvajal is a undergraduate researcher that's been helping us with a lot of projects, as has Athena Anchia. And she's a PhD candidate here at OSU. And then Michael Moses is our kind of primary state partner, works for Oregon's Coastal Management Program, and I'll talk about his contributions a little bit later. So the original plan was all 9 of us were going to talk for about 2 minutes each, but then luckily cooler heads prevailed. But unfortunately, what that means is you guys are stuck with me today. So I'll get on with the talk. So I think we're all pretty well aware now that coastal communities are increasingly exposed to flooding that's driven by a variety of different processes, both forced from the ocean as well as from watersheds. So in estuaries, we've got tides, waves, storm surge kind of propagating up into the estuaries and rivers. Well, we've got river discharge and precipitation, and all of these processes are combining to shape flood behavior and impact. So these are a couple of photographs during some of the kind of recent flooding events in Yaquina Bay, Oregon. But these kind of pictures have been taken anywhere in any Pacific Northwest estuary over recent years, so causing lots of problems for the communities that are living in these areas that are impacted by compound coastal flooding. So again, I think we're all kind of well aware compound coastal flooding amplifies the impacts, and so that are being experienced by these coastal communities. We know that extreme compound flooding does not require each individual driver to be extreme, and this is really true on West Coast estuaries where we don't have significant storm surge associated with tropical cyclones. So it's moderate combinations of things like surge, discharge, precipitation, and some of the wave forcing that can produce severe flooding with just unfavorable timing and duration of those processes. And there's been a lot of work that's demonstrated that over the last couple of years. But certainly climate change is expected to intensify what's going on both on the terrestrial side with heavy precipitation and runoff, but also we've got sea level rise plus climate change impacting, again, all of the processes from the ocean side as well. So we need to take into account climate change to think about coastal risk into the future. There's also a lot of limitations of kind of our current flood risk methodologies. As Katie Seraphin has said many times, Mother Nature has only rolled the dice once in our short observational record, and that kind of limits our ability to characterize multivariate extremes. Many flood risk assessments rely on deterministic design events that treat drivers independently rather than looking at the full combination of all of these different drivers in compound flooding. So here's just a couple of pictures of the kinds of things that the Pacific Northwest experienced just this past winter, with king tides causing significant coastal flooding in estuaries, as well as the influence of heavy precipitation for some of our atmospheric rivers. And it's the co-occurrence of these kinds of events that cause greater flood extent and severity that need to be accounted for in flood risk methodologies. So we've been working towards various approaches for probabilistic flood modeling for quite some time. And these approaches are taking a response-based approach. And the idea is to simulate many combinations of the different flood drivers and compute the resulting impacts and risk rather than just simply looking at individual events and scenarios. To capture the full range of possible conditions, this means that we need to have hundreds, thousands of scenarios explored rather than just a handful, which has been kind of some of the traditional approaches. However, that raises problems because our typical high fidelity hydrodynamic models are often too computationally expensive to run for all of the scenarios necessary to really kind of get at this kind of multivariate risk. And so these are a variety of challenges, among others, that motivate our desire to develop scalable probabilistic frameworks that link climate variability to compound flood response. And I give a couple of citations at the bottom that are kind of the work that we've been building upon in this effort here. So again, we're after, with this project, a scalable probabilistic framework that it allows us to directly link climate change and variability to flood response. Here's kind of a straightforward kind of diagram illustrating our general approach. We're starting kind of at the center of this, working with a reduced physics flood model rather than a high fidelity numerical model, which allows us to look at a lot longer time series, et cetera, to kind of get at our compound flooding analysis. And we're going to start with historical observations or reanalysis fields and generate kind of long time scales of hindcasts of these compound coastal flooding. It's a pretty straightforward framework. One thing that we're bringing to the table is, again, because Mother Nature only rolled the dice once in our relatively short observational time period, we have what we've been developing over the last several years, a multi-scale climate emulator. We refer to that now called MUSCLE. And that's an approach that allows us to generate plausible time series of the drivers relevant for coastal flooding in these estuaries and coastal systems. So this stochastic climate emulator has been developed in deep collaboration with Fernando Mendez's GeoOcean group at the University of Cantabria. And it allows us to basically roll the dice many, many times and again, develop these plausible time series. So we can actually truly develop probabilistic response-based compound coastal flooding analyses by passing the time series from this emulator through, again, the reduced physics model, okay? So as I mentioned, we're applying this technique to the north central Oregon coast. Many people might be familiar with the city of Newport, Oregon. And so this is the Yaquina Bay River and the Yaquina River and the Yaquina Bay estuary. So the model is forced on the ocean side with the typical culprits of tide, storm surge, monthly mean sea level anomaly, wave climate. On the terrestrial side, we have precipitation causing overland flow, infiltration, et cetera, resulting in added water levels to the domain. And we also have a long time series of river discharge at the offshore boundary condition as well. So these are the way, this is how the model is set up. I'm not going to spend a lot of time demonstrating that we've kind of validated the model against a variety of different measurements. On that last slide, you might have noticed a bunch of blue dots that I didn't point out. But these are areas where there's either been long-term tide gauges or a handful of pressure sensors that we've helped, our group has helped maintain over the last several years. And some of them are in relatively straightforward places to model total water levels. Others are in more complicated backwater sloughs, et cetera. And here's just a couple of examples of observations over about a fortnight showing that this is an event in 2022 where there was strong surge, relatively heavy precipitation and high discharge. We were able to really do a nice job with the model of reproducing water levels right near the inlet, but also in Pool Slough is a little bit more of a complicated area. And Sphinx also does a pretty nice job of reproducing the water levels there as well. And we've got a variety of other kinds of products that we've developed to demonstrate validation. I'll point out that we also have in these slides AdCirc simulations. So it's a high fidelity model that we've also applied to this location. Of course, that model also does a very good job of reproducing the conditions that are observed. The thing I'll point out is that Sphinx takes 3 minutes for this simulation, where AdCirc took orders of magnitude longer. Okay. So we've got this set up now. We've got a straightforward experimental design that, we're really kind of looking to do a hindcast with historical observations. So that's the first thing we're doing. Just all the individual drivers that I pointed out in that cartoon are just driven through in a time series mode, hourly time series mode, to kind of hindcast water levels throughout the bay. And then we have ensemble simulations that are generated with our synthetic tool, this MUSCLE climate emulator. So we have two approaches for generating basically today's climate coastal flood risk throughout the estuary. And so I'm just going to give a couple of simple, straightforward examples here. Ultimately, we're going to be working with the full 40 to 50 year observational time period, but we're still kind of tweaking little bits and pieces of the model. So we're starting with just a 10-year hourly simulation, 1980 to 1990. The boundary conditions, again, are from observations and reanalysis products. This simulation took about 15 hours to run this 10 years. So basically, really demonstrates that we can run multi-decades through this setup. What the product that's being shown here is basically the probability of inundation kind of at a daily scale over this decadal time period. So obviously the areas that are these bright blues are areas within the kind of the thalweg, deep parts of the estuary that are always wetted. But then you can see some of these lighter colors in areas that are only wetted during high tide or even during extreme events. So this is just one way to kind of visualize the ability of this model to kind of produce time series of flooding on an hourly scale for a decade time period. Let's zoom into an area that's a little bit maybe more complex. And this is an area upstream, kind of a slough that's connected to the main estuary by a culvert, but it has a road that goes along that area that is occasionally impacted by high water levels, and that's what that red dot means. I'll come back to that in a little bit. But this is just a zoom in, basically showing again that the areas that are wetted relatively frequently versus areas that are infrequently wetted, and kind of get a really nice sense of the areas that might be flooded only during extreme kinds of conditions here. With this kind of modeling approach, we can obviously do a lot of different things. Here's Carson has just extracted the number of days per year in which there was ankle deep water levels, so a little bit greater than 10 centimeters. So potentially the water levels high enough to kind of cause problems for local community members. And we can actually look at individual events. These are driven by observations. This time period covered the 1982-83 El Nino, which had elevated water levels throughout the Northeast Pacific. And this was one event that there was, at least the model suggests, there was 14 centimeters of water on the road in January of 1983. Three occurrences actually over this full decade that we're simulating with this model. Now we know that this is an area of problem for local community members because of this red dot. This is an identified resilience project in Lincoln County, and I'm going to talk a little bit about the stakeholder engagement project in just a couple of slides. But the nice thing we can do, again, we're running observations through this numerical model. We can look at the three different events that did cause overtopping of this road and causing basically a little bit of islanding for the communities that were trying to move along the estuary during that time period. The road elevation is a little bit below 3.5 meters. Here are the three events that were higher than 3.5 meters in that modeled decade, and we can look at the relative influence of the different forcing conditions. And so it wasn't the highest tide event that caused the biggest flooding event. It was a combination of storm surge and sea level anomalies, as well as relatively high discharge. And this is just looking at the actual the observational forcing during the time period, but we can, over the length of the time series that we're analyzing, we can look at the relative influence of these different processes to coastal flooding events. Okay, so that was running just a decade of observations through the modeling system, and I mentioned that we have this stochastic climate emulator. We're able to reproduce plausible time series of the different drivers that are necessary to run the model. And so here's a result where that basically it's another 10-year period representing today's climate, but driven by muscle. Again, it takes 15 hours to run this time series, the same product. We can zoom into the same location. We get the same kind of product for now a synthetic time series of representing today's climate. The nice thing is we can actually look at the differences. Obviously, this is not going to be, we're not reproducing the observations exactly here. We want to see differences, but we can actually run now an infinite combination of these muscle simulations and really kind of develop robust flooding statistics. We expect to see differences like this, but the fact that the flooding statistics are so similar, basically, and this is just a difference between the muscle simulation versus the observational simulation, again, with a 10-year period, basically just suggests that the muscle is capturing the characteristics of the flood driver pretty well. So we're pretty happy with that. And we're moving forward with many, many multi-decadal simulations from that approach. So We've got observations and an emulator running through the model. What kinds of things can we learn from this? Well, from the observation-driven simulations, we can learn, of course, where the flooding occurred, how often, how deep things get, how problematic these flooding issues are. Which are the individual forcing conditions that are driving most of the flooding events. That's kind of the future work. It allows us the ability to analyze specific storm events. But by now working with the stochastic emulator, it allows us to think about not just what did happen, but what actually could potentially happen, even just thinking about today's climate. Again, we only had one single realization of history, so of course the rare and extreme events are undersampled. With the emulator, we now have the potential of many plausible realizations of the same climate, simulate a variety of events and flood extents that are not seen in the observations, and build, as I just said, robust statistics. All right, so this is moving forward right here, but the nice thing, well, this is just, kind of just summarizes what I just said with this modeling framework. But one of the main goals of this particular user-funded project was to connect directly climate change to the mussel framework, right? So it's, as we, I think, all are aware, it's relatively easy to add sea level rise scenarios to a coastal flooding framework and look at the impact of just sea level rise only. But climate change is going to have an impact on every single process that I've mentioned, from the precipitation to the river flows, to the waves, to the sea level anomalies, et cetera. And so we've spent a lot of time, this is work that's been led by PhD student Nate Philman, advised by David Roop, where we've connected directly CMIP6 GCM modeling scenarios to the mussel framework. Now, I don't have time to kind of go into the details, but we basically picked the 8 best GCMs in the CMIP6 suite that represent the kind of the physics associated with hazards in the Pacific Northwest. And these are things like the influence of El Niños on precipitation and sea level anomalies. So we did a lot of pre-work identifying what the best models were. We're looking at a range of different scenarios, SSPs from those CMIP6, and we've connected those models directly to our mussel framework to allow us to now develop plausible scenarios of future climate. We're calling that now mussel future. And with the different ensemble runs, with these different scenarios and different models, we have at least about 160 approximately century scale scenarios that we can run through the modeling framework. So again, this just kind of repeats what we just said, but we now have the ability to do this for future climates as well. And so this is just now a 10-year simulation, the same kind of product I showed you earlier, but this is just picking one simulation from one model, one scenario. This is the UK Earth Systems model at the end of the century without any sea level rise. Again, we're seeing very similar products. It turns out that in this 10-year simulation at the end of the century, we only have 2 road overtopping events rather than the 3 during the observational period. And so this is something that we can explore multiple models, multiple scenarios, and see how robust those statistics are. Of course, as I mentioned earlier, I'm just going to show you this one result from one of the climate scenario models. But we can easily add sea level rise to this as well. So this is just adding 1 meter of sea level rise by the end of the century for that 10-year-long simulation. Again, the probability of inundation at kind of at daily scale, and I just flip back and forth between these 2 products. And you see areas that are very infrequently wetted in some of these sloughs inside the estuary become, obviously much darker blue with sea level rise. So we can explore the influence of climate change in a variety of different processes through the lens of probabilistic coastal flooding. All right, so, and back to the road overtopping, we had a couple of events in the observational period. Well, with this 1 meter of sea level rise, it looks like there'll be about 130 days. Obviously very problematic to the coastal communities that live in this location. So these red dots that I've been showing on these maps are actual areas that are basically potential focus areas for adaptation projects, some of which are actually starting to be initiated now. And this is a result of a fairly deep engagement process that was led by the state of Oregon. Michael Moses has a process called ARAP, kind of estuarine resilience planning process. But here's a picture of both Carson and Nate presenting to a stakeholder group as part of this ARAP process, some of the initial modeling results, getting some feedback on the way that the data sets are being presented, getting some feedback on where some of these adaptation projects might be. And this, we participated in several of these kind of listening sessions, interacted with this group in terms of some initial modeling results. And we basically have a list of these kind of a suite of candidate adaptation projects in the region. Here's just a kind of a small non-exhaustive list of those things like upgrading culverts, kind of a typical way to modify potential floods, floodplain restoration. Obviously, the road that's being inundated occasionally now, they're thinking about elevating that road. But one of the more exciting projects is a potential tide gate modification or removal of this kind of oxbow right here in the middle of the domain. This area obviously was originally had the tide gates for grazing and agriculture. But it was this area, this land was recently purchased by a land trust and is eventually going to be ceded over to the Siletz Indian Nation. And they're truly thinking about potentially modifying or removing the tide gates and allowing salt water to kind of flood into an area that has been restricted for decades. And so we'll look at the influence. Obviously, with this model framework, it's relatively straightforward to make some modifications on the landscape. And so here's again a synthetic future simulation, the same kind of products, 10-year simulations, look at the probability of daily inundation. On the left, it's with the existing tide gates as best of our ability to model them. But on the right-hand side, you see the influence of removing those tide gates. So obviously, these dark blues in the oxbow are the influence of now estuarine water kind of getting back up into the area that they're thinking about restoring. And we could look at the differences in the daily inundation probabilities with and without the adaptation scenario in the model. And we really, obviously increase the amount of water in that oxbow, but really interestingly, decrease the flooding days in other parts of the estuary. In particular, that road that gets overtopped gets slightly decreased water levels, which actually reduces the amount of overtopping. So one impact on the estuary in one location would have big implications elsewhere. All right, so I need to wrap up here. Jenna is about to tell me to stop talking. I mentioned all this. We've got a probabilistic framework that links climate to the drivers of coastal flooding to flood response. The climate emulator and hydrodynamic model allows us to explore a full range of compound flooding conditions. And we're doing a variety of, we think, pretty cool things with this. I wanted to end by saying that we've also spent a lot of time trying to develop some tools in a way to kind of deliver this information to groups like that ARAP group that I mentioned earlier. So here's an initial effort of an online flooding tool that really will serve the data that Carson and others are developing as part of the modeling. And then here's a example of a story map. We also have one-pagers that are being developed in both English and Spanish language to get this information out to as wide a variety of audience as we possibly can. So with that, I'll stop. Thanks.
Thank you, Peter. That was great. Very great. Yeah, Nicole says, excellent, so useful to coastal communities. Yeah, it's great to see the basic research and the different applied research and then actually translating it to the communities. I don't see any questions yet. I got a shout out.
I have a question.
Road Brain. Oh yeah, sure, go ahead.
Hi, Peter. Nice presentation, and thanks for sharing the results. All these projects, very interesting projects. A quick question on Sphinx simulation. So when you compare Sphinx versus AtCirc, you get very similar results, but Sphinx is I could see significantly cheaper computationally, like 6 minutes versus 6 hours. I was wondering if in Sphinx, do you turn off the nonlinear convective terms? That's why it's very cheaper computationally, or you run it on GPU or more computational cores. I was wondering what is the reason they are significantly different, 6 minutes versus 6 hours.
Yeah, we probably talk for a while about the details, and it would be great to have Carson and others kind of chime in here. But yes, primarily, I think the big difference is starting with getting rid of some of the advective terms, the nonlinear terms that you mentioned is a big savings. And so far, we found that it's doing a decent job. We are comparing AdCirc and Sphinx to a variety of observational stations, as well as we're trying to also compare to some satellite products of coastal flood extents. I haven't shown that here, but that's work that's ongoing. So I think for kind of these general, full estuary products, we feel like Sphinx does a really nice job of kind of giving us the general sense. Kind of diving into some of the details and some of these complex areas, we're probably missing some of the important details, and I think we still have a lot to learn in terms of how far we can take Sphinx.
Sure, got it. Thank you.
Thanks, Peter. Yep, Philip, you want to ask your
I
question?
had the same question, Reza. We're practically in the same building here. And so you have the nonlinear. I mean, that's normal with Sphinx. You don't have the nonlinear. It calls it advection, even though it's not like you're neglecting advection, right? You're neglecting the nonlinear terms. We've been learning Sphinx too, and so I was thinking the same thing. So and the same thought I had was, are you validating against high water marks? I know from my experience when I simulated Jamaica Bay a lot in the past, when you have a small domain, your model, even if you change your bed drag, like it doesn't change the results that much because it's a small domain. So I think that's one reason you can do pretty well. But it occurred to me that, yeah, high water mark, in deep water, you'll do well, but maybe you could try simulating a storm or a spring tide or something with advection turned on. That might be worth looking at, I guess. Do you use the subgridding capability and of course resolution like grid with subgridding?
Yes. Yeah, and I'm gonna Carson can maybe add to the chat if he's here, but I think it's a 5 meter subgrid, but we start with a coarse grid. So yeah, a lot of the actual computational time is going from the coarse grid to the fine grid, but that was built into those estimates that I gave. We are working with some GPU simulations, so we're kind of experimenting with trying to get as much of this done on GPU, but Sphinx is not perfectly set up for those workflows quite yet. But we're experimenting with a lot of different ways to make this go fast. Because you saw that climate change experiment where we would love to see multiple models, multiple scenarios, et cetera, over decades. And so,
amazing work. Thanks.
Thank you, sir.
Yeah, Angelica, if you want to ask your question real quick.
Hi, Peter. I really love this work. First, a comment. I would love to talk to you about satellite data comparisons if you ever want to chat. But my question is, given my naivety about Sphinx, I don't know if this is an out of bounds question, but is there utility of this tool in salinity intrusion?
I'd love to have somebody from Deltaris that likes to play in the details to answer that question. Definitely, I've never seen an application that is working in kind of vertical dimensions. I think it's been mostly 2D. So my initial answer is no, but I've also learned to never say no when Deltaris is developing models.
Yeah, it looks like we had a comment that it's 2D only. Well, great. That's great discussion and good to see all the feedback and for Peter, and might be an interesting year for your El Nino situation. So yeah,
we'll see some scenarios to run. Yeah.
Yeah. Well, great work. Keep it up. And with that, we'll move to our next presentation. If you want to go ahead and pull up your slides, our next presentation will be by Dr. Justin Stopa and his student Lydia Rice, working on an investigation of morphodynamic long-term variability at Waikiki Beach. So take it away.
Hi, thank you for the introduction. My name is Lydia Rice. I'm a student in Ocean and Resources Engineering at the University of Hawaii at Manoa, and today I'm going to be presenting alongside Dr. Justin Stopa. We are actually at the end of our no-cost extension to the first year of this project, and we were able to give a kind of a progress review last September. So today we're going to be focusing on our updates since that last presentation, specifically looking at a comparison of tropical and temperate beach morphology. Before I get deep into the research, I wanted to start with an overview of the two sites that we're going to be talking about as part of this research. So being in Hawaii, the most important beach that we've been studying as part of this research is Waikiki Beach. So it's located on the south shore of Oahu. You can see it on the map on the bottom left-hand corner here. It's characterized by a steep slope and a fringing reef. And here in Hawaii, we have a really weak wave seasonality. So we're not seeing a lot of variability from season to season in the wave climate here. And that's really important when we're looking at coastal applications. For the data set here, we have a series of weekly surveys that were collected by the Coastal Geology Group, or now the Coastal Research Collaborative here at the University of Hawaii, where they completed weekly aerial and ground surveys. And through this, they generated digital elevation models and were able to calculate beach volume on a week-by-week basis. And we have the time series of that on the top right corner here. Our comparative study to represent our temperate beach is Duck, North Carolina. And a lot of you may be familiar with this if you're familiar with Army Corps or the U.S. Army Corps of Engineers work. They have the field research facility out there. This is a starkly contrasting environment to the beach in Waikiki. It's much more mildly sloped and there's a lot more seasonality in the wave climate. So it's different in both environment and climate. Here we have a little bit more frequent of data. There's hourly LiDAR scans that are completed by Duck FRF. And through these, we've taken the DEMs and have been able to calculate a week or a daily volume. So we averaged it out and then we detrended to remove the impacts of tides and nourishment in the local area. And so we can see a comparison of those time series on the right as well. I also just wanted to give a brief view of what Waikiki looks like so we can kind of understand why we're studying it. Here's some images from that survey that we're using for our data set. It is fronted by a lot of hotels. It's frequented by tourists. It's really important. There's a lot of, it's a big impact on the tourism economy here. So there's a lot of interest here in the state of Hawaii in understanding why it erodes the way it does. For the first year of this project, we had a couple of different questions that we wanted to answer and some objectives we wanted to reach as well. So the first research question that we wanted to address as part of this research is there a relationship between the offshore wave conditions and sediment transport at Waikiki Beach? And if so, what sea state parameters are important to sediment transport? Next, we want to address what role the antecedent beach state plays in the sand movement. So do previous conditions affect current conditions? And finally, we want to understand how these results compare to the beach in Duck, North Carolina. So the first objective kind of talks about all three of these. So essentially, we want to identify and quantify how beach change relates to wave forcing at different time scales. And so in doing this, we basically are performing an analysis that I'll talk a little bit more in the details in the next slide, but also look at what time scale of antecedent conditions impacts the beach state at both a tropical and a temperate location. We also spent some time developing empirical models that can predict beach characteristics, specifically at Waikiki, and we use these to be able to predict beach based on offshore wave conditions and also water level forcing. The majority of the research we're doing in this project is built upon Dr. Stopa's previous student, Julianne Kalksma's thesis, which she completed in 2021. In her thesis, she was able to identify key relationships between wave forcing and beach variability at Waikiki Beach, essentially confirming that yes, offshore wave forcing does drive changes in the beach volume, which allows us to go into the further stages of our research with confidence that the relationship we're looking at is meaningful. There's also a lot of previous studies that have been completed in coastal applications that have demonstrated the antecedent or previous beach conditions play an important role in the previous beach state, or in the current beach state. An example of this is in Waimea Bay, which is on the north shore of Oahu, as well as a series of studies that have been completed across the Gold Coast in Australia. We're able to emulate these studies by using a power of 10 filtering application. So essentially what we do is we take the wave time series that we have, often in these scenarios from a hindcast, and we apply a power of 10 filter to it. So we identify or choose the time frame of relevant conditions that we want to look at prior to the current beach state. And then we also choose a weighting factor so we can understand at what point it reduces to about 10% weight. We apply this filter to the wave time series, and then we're able to perform a correlation analysis. And that allows us to correlate both the original time series and the impacts of previous conditions on the current beach state. And we can kind of see what that looks like on the actual time series on the right here, where we really kind of capture the major trends as opposed to very short-term variability. Following up on Julianne Kalksma's work, we were able to apply this correlation and filtering analysis across the entire wave spectrum that's relevant here in Waikiki. So we have two examples of this up at the right. So on the left side, we have direct correlation, so just correlating the wave energy density directly to the beach volume. And then we have the filtered wave energy density, so filtered to consider antecedent conditions, then correlated with beach volume. What we found is really interesting. So off the bat, we do see that there is a relationship between the offshore wave forcing and the beach volume, which is something that we had already confirmed in previous research. But what we also see is that as we increase the filtering length and we add that filter and consider antecedent conditions, the strength of the relationship really increases. So what this means is that memory is important, that the Waikiki Beach's variability considers previous states. It's still responding to previous conditions, and therefore we can't just look at the waves today to understand why the beach looks like how it does today. We've also been able to identify some key patterns, and we've done this by looking both at the wave spectrum and at some individual beach characteristics, such as wave energy flux, peak energy direction, wave height, and wave period. And we basically identified that the southern and the western wave regimes, so the southern swells that we get year round, and then some western waves that we get that are associated with what we call Kona storms, generally have a positive relationship with the beach volume, indicating that those conditions tend to improve the beach condition or lead to accretion. On the opposite side, we have wind waves that are generated by the easterly trade winds here in Oahu, and those are generally associated with erosion of the beach, and that's why we see that pocket of blue on the wave spectrum there. So understanding that beach memory is important and understanding that there is some correlation with different types of waves that has to do with what relationship we're seeing, we're able to then focus in on individual wave characteristics and use those to really investigate what length of memory is important in Waikiki. So first, we identified the two key wave characteristics that have the strongest relationship with beach volume. And those two characteristics are the peak wave direction and the height of those eastern wind waves that we're seeing. So what we did is we applied a series of different filter lengths, ranging from a couple of months up to an entire year. And we compared the correlation coefficient with each of those filtering lengths. And you can see those here on the plot. We have the peak wave direction on the left, and then the eastern wind wave height on the right. So essentially what we see is as we increase the length of the memory, we're seeing a stronger relationship, indicating that there's a pretty significant length of time that is relevant to the current beach state. Ultimately, we found that at least a year of antecedent conditions are relevant to the current beach state. We do think that it could possibly be longer, but unfortunately we only have 3 years of survey data, so we're kind of limited in how long of a filtering period we can test. This also revealed to us that there are two key relationships. So with the peak wave direction, we found that when the peak waves are more south-southwest, we see an increase in beach volume. When they're more south-southeast, we see a decrease in beach volume. So there's a positive correlation with the direction and the beach volume. And we're seeing about a correlation coefficient of R equals 0.74 with that full 1 year time frame. On the other hand, the eastern wave height has a negative correlation. So as those wind waves are taller, we see more erosion, and as they're shorter, we see less erosion or even accretion. And we see a correlation coefficient of negative 0.71 with that. With this all figured out in Waikiki, we were then able to move forward and perform the same assessment in Duck, North Carolina. And what we found was really interesting. So we've identified that offshore wave conditions are really important for driving beach volume in Waikiki, but conversely, in Duck, it's really not nearly as important of a relationship. So on the right-hand side here, we have the Waikiki peak direction and the wave height, and then we have two key characteristics we selected for Duck, and we've both correlated them with and without the filter. And what we're seeing is we're seeing really, really strong correlation coefficients in Waikiki, and we're seeing relatively weak correlation coefficients in Duck. And what this means is that offshore wave conditions do not drive the beach volume at a temperate beach like Duck the same way that they do in Waikiki. Another finding that we found was that Duck has a shorter memory. So we optimized the length of the memory the same way we did in Waikiki. And we found that about a month of memory is where we see the strongest correlation coefficients. And after that, the strength of the relationship actually tends to decrease. This is consistent with previous findings from both Waimea and the Gold Coast, which found that more seasonal beaches tend to have much shorter memory lengths. And this is because the strong seasonal variability tends to wash out the effects of previous conditions. So essentially, this confirms to us that memory plays a stronger role in Waikiki than in other locations. And this is really important for coastal applications when we're understanding why the beach changes the way it does. We need to look at the past and not just at current conditions or even a week behind. We need to look at the past year of conditions that we have. With this understanding, we then move forward to the next step of our research, which is developing an empirical model to predict variability at Waikiki Beach. We tried a couple of different methods, but we ended up selecting a multivariate linear regression as the strongest method for being able to predict beach volume. Essentially, we selected a series of different wave parameters, wave height, energy flux, direction, and so on, and we put them into a series of linear regressions and continued to tune it until we were able to find a strong relationship that could accurately predict trends in the beach volume. What we ended up finding is that a combination of both the eastern wave heights, so the wind waves, and the western wave heights, so those are associated with the Kona storms from the west, has the strongest ability to predict beach volume. But what was really important is that this strong relationship is only found when we also include beach memory. So we include both the original series and the filtered series. But when you don't include the filtered series, the strength of the relationship drastically decreases. So with this, we were able to predict beach volume with an R squared value of up to 0.73. And this is really important because this can provide a really strong tool, a predictive tool for understanding the beach and predicting how it's going to change for coastal applications. We've also continued to develop this with other inputs excluded, like on top of offshore wave conditions. And the one we've seen the most interesting results with is actually with the water level. So here in Hawaii and in a lot of other coastal areas, we have passing eddies that result in changes in the water level. Essentially, the eddies result in a higher water level, so we see a difference in the observed water level and the tides that are predicted based on the surrounding environment. These changes can last for weeks to months, and they're often really visible on the tide gauge data. And you can see this on the top right corner here. So in the red, we have the NOAA predicted tides here at Honolulu. And in the blue, we have what the actual observed tides are. So here in December 2020, there was clearly an eddy passing by that resulted in a much higher water level than was expected based solely on the tides. We were able to calculate the tidal residual, which is the observed minus the predicted tides. And that difference in water level has actually we found it to have a really strong impact on the beach volume. So we did a similar correlation analysis and found a strong relationship. So we decided to move forward and include it in our empirical model. We did the same process where we included both the original time series and the filtered time series. And what we ended up finding is that it really strengthened our model. And we're now getting an R squared value of up to 0.83. This is really significant because it shows that there are also other things we can consider in our predictive analysis other than offshore wave conditions. This is really interesting, and it's something we are hoping to continue to work on. And I actually have a fellowship through the Hawaii Data Science Institute where I'll be continuing this research with our goal of being able to predict additional factors such as shorelines and spatial profiles on top of just the beach volume. I'm now going to pass it over to Dr. Stopa, who's going to be talking about some of our summary metrics and stakeholders for this project.
Thanks, Lydia. Can you go to the next slide, please? Yeah, so we have some really important key partners here. Chip Fletcher, he's the main PI who collected that data. He's also now the dean of our school. Anna Mickelson, who works with Chip, who is a big part of collecting all that data. Dolan Ebersol, he is the Waikiki beach manager, and he's coordinator really of that whole area. And he sits on campus, which is great because we have access to him. And then also we have ongoing conversations with Dolan. They collected a few more surveys, so we're really interested to collaborate with him on those because we'll be able to test our empirical model a bit more with nice held out data. Because really we are concerned that we just have, of course, these 3 years of data, and when we're trying to extrapolate beyond that, we might be missing a lot of the key climate features as we just saw that are extremely rare, right? So we do understand that that is a limitation. So as far as metrics go, Lydia really has been trained, and she has been supported by this project for the last year. We do have a manuscript in preparation. We're really in final stages of that. Lydia has also given some nice presentations locally here. So she's given a seminar here in our department, and she's also been working with a local middle school here, giving some results that were supported by this work. So I'll just conclude with where we are in the timeline here. So we're in our extension year of year 1. So we're really just wrapping up this empirical model. And then year 2, really our objective was to look at more of the long decadal time series. And what we would do is use the model that we were just describing to really extrapolate that. We do have some other key held out data for that. And that is through aerial surveys taken by planes. We don't have too many of those, but they do extend back into maybe the 1950s. And there's maybe at least every decade, we at least get one of those snapshots. So we would be using the model we developed in addition to all the other observational data we can get our hands on to first assess that model, and then really just look at the variability by driving it from an offshore condition from a wave hindcast, and then use that as a proxy to determine what the beach variability was like over the past several decades. So thanks if you have questions for us.
Awesome. Great. Thank you, Justin. And thank you, Lydia. Great presentation. And congrats on your fellowship, Lydia, to continue working.
Thank you.
Yeah. I don't see any questions in the chat yet, but if anyone has one, oh, here we go. Savannah. Yeah, feel free to.
Yeah, hi, thanks, Lydia. That was great. I am currently a postdoc here at the FRF, and I'm working on equilibrium shoreline modeling. So I'm really familiar with this LiDAR data set. And I'm curious how you said you sort of dealt with the two nourishment events that happened for the duck data set. And what we actually see is that there's like a southward propagation of that volume because the nourishment events took place north of the FRF property. So did you take into account any sort of delay or timescales of transport in order to deal with that?
Yes, we did. And I may have it in an appendix here. Actually, I didn't end up including it. But essentially what we did is we took the total time series and were able to identify the time frames of each of those nourishments. And we ended up breaking it up, and we found that before a nourishment, we saw a general trend in erosion. And then for a certain period of time after the nourishment, there was a jump and then a different trend. And then it eventually leveled out to about the same linear erosion. And so what we ended up doing was we detrended the data. So we removed the deviation from that trend in the periods of time that were immediately following the nourishments and basically leveled everything out to a more normalized volume. And then we also did averaging to remove, because it is so frequent data, we also had to do some averaging to remove tidal effects. So that's what we ended up doing. But it was really interesting looking at that. And I think if we were a little bit more focused on Duck 2, we probably would continue to do everything we could to make sure, look a little bit more spatially to see how that impacted it and see if different parts of the beach were affected differently. But I do think that would be really interesting to look at further.
Yeah, thanks.
Mhm.
Thanks. Yeah, Peter.
Yeah, great talk, Lydia and Justin. Very cool stuff. Got just a brief comment and then a question. I'll start with a comment. I'm sure you've already seen the work by Sean Vatusek, and you guys probably know him. He was one of Chip's students. He's done some really cool work recently, just demonstrating that equilibrium shoreline models are really just convolutions, which is exactly what you're saying in terms of this memory component. And that convolution aspect is kind of the ability to tune the memory of the different processes. So if you haven't looked at that work yet, definitely take a look. Along those lines, maybe I have this wrong and I wasn't paying close enough attention, but it looked like when you were showing your correlations, the wave direction was one of the more important terms. But then that final kind of model that you had put together had just looked like it was just wave heights. I mean, they were coming from different directions, but so is that how you're incorporating the wave direction into it? Is via the wave climates being separated?
Yeah, so we kind of actually ended up approaching the empirical model with a fresh set of eyes. So we didn't want to necessarily come in with the exact same set of parameters. We did test them, but ultimately what we found is that when we're looking at this prediction, we're seeing a little bit different of relationships. But what is also important here to consider is, so with the peak direction, we're seeing, obviously, if things are coming more east, we're seeing negative, more west, we're seeing positive. We are kind of representing two opposite directions on this. So we're seeing the western events and the eastern events. It's not exactly the same as the peak direction, but that was something interesting that we noted, is that it's not exactly the same sets of effects. And when we actually looked at it, and we kind of talked about this in our last presentation, there's different spatial signatures for each correlation event too. And I think that probably has something to do with the predicted capabilities, because if it's moving sand, but not necessarily taking sand off and on, it may not be as helpful here in the model. So yeah, that was something that was really interesting. But yeah, it does. We were not necessarily expecting it to not have as strong of an impact. So it was a unique result, I think.
I'd like to just add one thing too. Yeah, to answer your question, they are the partition quantities. So we actually look into the just that sector, like frequency and direction bin to calculate those different wave heights.
That's great. Yep. And I see that you saw the message from Angelica about Phil Thompson, Mark Merrifield, and I have a NASA-funded project specifically looking at the contribution of eddy variability to extreme water levels around the Hawaiian Islands. Would love to chat more. So that sounds like a great connection.
Absolutely.
Awesome. And then Peter put a link in the chat by a paper by Sean Fatusek he was talking about, if anyone else is interested. Yeah, and looks like that's all the questions in the chat. And I guess with that, yeah, we'll just again thank our speakers for your presentations today and your contributions to USCRP and the coastal community. You guys presented some really great work today that's having a great impact on the community. So thank you very much. And with that, we'll end our meeting today and look out for our June USCRP newsletter with more updates via email. And we'll see you next month. Thank you very much.
Thanks a lot for having us.